Today I'm going to present our work, passive 3D time-of-flight imaging, leveraging VLC infrastructure. So let me share my presentation. This work is carried out with the collaboration of CiTIUS, University of Santiago de Compostela, Spain, and pmdtechnologies AG Siegen in Germany. So let's start. My presentation outline is divided into the following sections. First of all, I will start with the introduction part. Later on, I will give a brief explanation of our methodology, the approach which is based on. After that, I will give some insights about our system model. Later on, I will show the experimental setup in proceeding slides. I will show simulation results and experimental results. Finally, I conclude my presentation and provide some future lines of work with the supporting references. So let's begin. The time-of-flight imaging is divided into two categories. One is active time-of-flight imaging and the passive time-of-flight imaging. So basically, a ToF camera is an active system that needs a dedicated illumination unit that illuminates the scene, and from there and that are able to estimate the depth from the reflections by exploiting the demodulation capabilities of demodulation signals. And based on that, in active time-of-flight imaging, the source and the ToF camera are closely integrated. There's no space between the ToF camera and the illumination source. And also, depending on the modulation waveforms, the ToF cameras are classified into two operational modes. One is the continuous wave, in which the periodic continuous wave signals are used for illumination and also used for demodulation control signal. In pulse wave, ideally the square pulses are used for illumination and the demodulation control signal. In this case, in our approach, we are exploiting pulse-based approach. So now I will give some overview on passive time-of-flight imaging. Passive systems are able to estimate the depth by processing the reflections, which are coming from the reflected from the target, and the target illuminated by the non-cooperative source of illumination in indoor or indoor environment, such as VLC or Li-Fi sources signals. And passive ToF cameras are basically two co-located receivers, a photodiode and a ToF camera, where one is responsible to get the synchronization signal, other is responsible to get the reflections. Passive configuration provides a biostatic geometry for passivation of the ToF modality. So what are the problems faced by the existing ToF cameras? One of them is a high power consumption, because a dedicated illumination unit consumes high power. Disturbance in the ToF measurements because of the background light and the temperature effects when the ToF module is continuously in use. So in this case, the visible light infrastructure is a suitable solution to address these problems which are faced by the existing ToF cameras. Now I will give some overview on the visible light communication, or the broader field is optical wireless communication. This VLC is basically a sub-branch of this optical wireless communication. VLC is high-speed communication technology that uses visible light spectrum. And also there is a Li-Fi, which is a light fidelity, which is based on the IR spectrum, and that provides that also work as a high-speed communication technology. In the last few years, the lighting infrastructure has transitioned from lamps to light-emitting diodes based on this LED-based infrastructure that can provide multiple services like illumination, communication, and now it may provide 3D sensing services. And in the past, the VLC and the time-of-flight sensing have developed independently in a wide range of applications. So in an attempt to make this intersection of both the independent developed technologies to obtain the new services without exploiting new resources. So we attempted to enable a process that eventually lead to a merger between the optical wireless communication industry and the time-of-flight imaging industry, to have a merger that allows us to attain the passive time-of-flight sensing services from these two intersection of different technologies in one point. So now moving ahead with the methodology, or the approach which our approach is based on. So the source, any source can generate a signal which is transmitted from the VLC emitter, and this also eliminates the scene. Also, this direct link is established between this emitter and the photodiode, and this photodiode signal received and moved towards the thresholding circuit, and this thresholded signal moved towards the delay generator, which enables custom delays, and then feed it to the PMD module or evaluation board. And on the other hand, this reflections are occurred by this PMD camera at pixel level. This PMD camera work as a cross correlator that cross correlate at pixel level to attain different number of measurements. As you can see on the right side of the figure, that this is basically our biostatic geometry, where there are two sensing channels. One is established. One is a direct link between the photodiode and the VLC emitter. Another one is indirect link between this illumination source and reflected from the target towards the ToF camera. By exploiting these properties, we are able to estimate the depth. So now moving to give you some insights on our system model. So now communication model is, we can say the downlink signal is which is received by the photodiode or any device in the environment. That is basically depending on the probing signal which we are providing based on that convolution operation between the data generated, which is known as X of t, and the LED impulse response that we get the probing signal. And when this probe signal is convoluted with the channel impulse response and with the additional additive white Gaussian noise, we will say that this is our downlink signal, or this also received by this photodiode. And on the other end, the ToF sensing model, which we are able to get the reflected signal, which is also illuminated by the probing signal we know it in the start. That probing signal with the channel impulse response in indirect link, which is we call it a single reflections from the target, which is based on this formulation. And this is convoluted, and then we will get the reflected. In order to attain the measurements, we cross-correlate this reflected signal with the thresholded signal, applying this thresholding operator based on this our received photodiode signal, and we get the thresholded version of the VLC signal, and we cross-correlate it to attain the measurements. So in order to emulate the whole passive sensing pipeline, we took the reference cross-correlation function and from the experimental data as a optical signal, and then exploited this by exploiting the downsampling operator and shifting operator definitions. We are able to attain the measurement and candidate test vectors. Once we get the measurement and test vectors, depending on number of measurements, we use 4 and 8 number of measurements, and n defines the total number of samples, and t defines the time period which we are sampling the whole range, and tau is the shift which is enabled, and r defines the short range, or we can say that number of samples which are divided, and then it will shift according to the test vector. So once we get these test vector and the measurement vector, we exploit the match filtering approach based on that this equation. We estimate the distance. This distance is not the true distance, because we are exploiting the biostatic geometry where our source is far from the ToF camera. So in order to define a biostatic geometry, biostatic geometry can be defined by the 3D loop side, which is depending on two distances between the emitter and the target, and receiver and target. So these two distances, which are important factors, and the loop side foci are basically a VLC emitter and the ToF sensor. And from there, you can see that 3D location of the target can be defined by this equation, where R is our 3D location of the receiver, UR is a unit vector, and DRT is the distance between the receiver and the target. And thanks to the lens calibration, from there we are able to get the lens normals and obtain the unit vector length normals, and also that these distances we are able to get, and from there we can get the true depth between the camera and the target, where DRT is the distance between the receiver and the target, and the DER is distance between emitter and the receiver components, or receiver. And CXCR are also the emitter and the receiver coordinate components, and the UR term is basically the unit vector, which these are the basically unit vector components defined by this formula. Interested one can go through the complete derivation of this biostatic geometric algorithm in our reference number 6. This is our experimental setup where you can see that optical rail is used to move the objects, move the components easily. Here you can see that our open VLC module illuminates the scene. Also, this direct link is established, and this optical signal is received by the received by the photodiode, and photodiode signal is thresholded, and then custom delays are enabled. After that, you can integrate this or feed this to the evaluation board that supports external referencing. And so now there are a few steps that needs to be carried out at the experiments. Hypothetically, we know the transmitter, emitter, and the receiver positions. So we place the emitter position at a specific location, and the reference photodiode is placed on top of the ToF camera that establish a direct link between the emitter and the photodiode. So this reference photodiode signal is inserted into the thresholding circuit that converts the analog signal into digital, because the evaluation board supports the digital waveforms from 0 to 1.8 volt. So the threshold signals are fed to the picosecond delay to enable the custom delays. So because in order to get the number of measurements, we will delay this, we enable the custom delays to obtain the different number of measurements. And the reflections are occurred by this PMD camera. The ToF camera is placed at one of the location as specified here on the optical rail, assuming that our reference signal, which we feed for the synchronization, which is basically a representation of the VLC signals. And once these signals are occurred from both ends, this PMD camera work as a cross correlator, performs a cross correlation operation, and by dialing the signal, we can obtain different number of measurements. In this case, one has to do to complete occur the complete reverse cross correlation function, and after that, once the cross correlation function is occurred for the specific time period scale which we want to exploit, after that we recorded the number of measurements and applying the match filtering approach to obtain the depth based on the target. Here, so our target is placed at far from the ToF evaluation board. So these are the simulation results where we use two modules, OpenVLC and Li-Fi, and also we attempted to achieve high accuracy with the minimum number of samples to exploit different number of sampling approaches with the uniform random sampling and sparse ruler sampling. Here you can see that we attain minimum or negligible error rate in comparison to different sampling approaches. We achieved better performance of uniform and random sampling in comparison to sparse ruler sampling, because sparse ruler has a mismatch between the fine grid and the grid required by the sparse ruler. So in comparison, in this case, that sparse ruler performance degrade. This one is the first 3D passive experimental results, where from on the left side you can see the record depth image. On the right side, this is a 3D point cloud of the target, where you can see that our target is basically a polar star, where we obtain the estimated depth. Now I will conclude my presentation. We explored the novel passive modality, where we explored the hidden synergy of independently developed two technologies, VLC and ToF imaging. The use of new paradigm network promises a flexible and scalable light interface and services, because this VLC infrastructure is increasing day by day, and that we have to exploit this opportunity to attain the passive ToF sensing services. Aiming to reduce the number of measurements, we use different sampling approaches for the attaining depth accuracy with the minimum number of samples, where we also recommend commented on that sparse ruler has some problems with because of mismatch. And our proof of concept witnessed that feasibility of passive ToF imaging. And our future work includes thresholding optimization, because threshold increases the problems in terms of delays. And also the VLC signals are not optimized for dual function waveform, dual functionality. So dual function waveform need to be designed, and further hardware evaluation is required in our future lines of work. That's all. And these are the references which we use for our work. And thank you for funding this project. And that's all from my side. Thank you for your listening. If you have any question or query, you can approach me via given email address from this platform. And that's all. Thank you.